Hello, this is Dr. Heidelberg, and our presentation today is related to sensors in mechatronics. We will follow the textbooks of Bolton, the fourth edition. The sequence of modules is shown over here. We're in module 1, discussing the introduction to mechatronics and sensors. Here's the list of the textbooks pages, total pages, and we will start with the textbook. In the first two chapters cover introduction, the mechatronic design process, measurement system, controls, and examples. In a sensors chapter, the book discusses definition, technologies, types, and selection process. In our lecture topic, which is highlighted over here, this is lecture 1, we'll discuss the introduction, course orientation, mechatronics disciplines, machine learning, business development, and examples. And in the sensor sections, we'll take a look at detailed industrial example, competitive options, sizing, and system connectivities in sensors. The introduction, which is also defined here as a course orientation, is given in this playlist link. There are 10 lessons, totally 90 minutes, and they pretty much walk us through the entire process of our learning in this course. This particular lecture will relate to sensors. And what we see here is that Intel defines the industrial companies which use sensors and edge. Edge meaning that the analysis of the data received from the sensors is done locally versus the cloud, which is done in remote, is done in order to keep machinery humming. It's the main objective. The layers of the technology going from the sensor to the edge or the cloud goes through gateways which receive data from several sensors of interest. They transmit it to the edge, local computing devices, or onto the cloud. There are several challenges related to sensor data monitoring. We have a list over here by Intel, which is related to getting reliable connectivity, the exponential data growth, which has to be handled, new data types of format, unnecessary data that may get into the system, the IT capabilities to handle it on, managing the data in the edge, which is locally with limited IT folks, or in the cloud, process the data at the source, sovereignty of the data, who owns it, increasing risk with such a vast amount of information, and also integrating the new data with existing systems. We see that the state-of-the-art applications for sensor data analysis is shown over here, is related to predictive maintenance, to asset management, and artificial intelligence and machine learning. Smart sensors are defined as sensors which collect data as well as have signal processing to reliably transmit it through the chain. They include machine vision, acceleration and tilt, electric and magnetic, leaks level detection, force and load and torque, strength and pressure, flow, chemical and gas, acoustic, sound, vibration, humidity and moisture, temperature, position, presence, proximity, motion, velocity, and displacement. The technology involved in sensor measurements are vast. That includes capacitive eddy currents, encoder, fiber optics, gyroscopic, Hall effect, inductive, and the list goes on, and the textbooks cover most of them. The manufacturers that provide us sensors to be integrated with our mechatronic system are listed in Sense2B. They include a list of over 2,000 manufacturers covering a vast area of sensor types, position, mechanical, dynamical, pressure, chemical, temperature, vision, inertial system, optical, electrical, magnetic, acoustic, data acquisition, and so on and so forth. The communications between sensors and the edge or the cloud pretty much is done to increasing levels with wireless communication. We see that the networks relate to the distance where the information is being transmitted to, where there is a personal area network, such as the wearables. There is a local area network, such as home automation. There's a metropolitan, like in campuses, and also a wide area network through the internet and satellites which surround the world. This is a simple diagram that shows how it works. We have wireless sensors that transmit signals through a gateway. The gateway transmits signals to a software, which may be local or maybe in remote. The software may in turn transmit back signals to the actuator in response to the decision made by the software as how to handle the information. And we see here an example of a sensor. The company is Renishaw. Renishaw is manufacturing many products, including encoders. And we see that the information which is included in typical data sheets are defining a very large amount of information which is needed in order to make a decision which type of sensor shall we use, and whether the cost performance of the sensor is competitive with other options. So the information included in the data sheets includes sensor type, the manufacturer, trade name, technology used, communication being used, whether it's absolute or relative sensing, the ease of installation, immunity to environment, resolution, speed, errors, noise, safety, ingress protection with environmental dust and water, and then the integrated displays where they have it available cables, connectors, pinouts, and mechanical drawings. We see here some specifications example of the sensor, whether we have it as a definition of the full scale measurements, the size of the sensor, the accuracy, and the sensitivity. For example, in this case, accuracy specified at 20 degrees C for RELA is plus or minus 1 micron up to 1 meter. And it goes plus or minus 4 microns in length of up to 5 meters. We see also the specification of a sensor related to environmental protection. For example, we see over here that the temperature environment with this, which this sensor can stand is minus 20 C to plus 80 C. It can operate from 0 to 80 C. Humidity, it can work at 95 relative humidity. In other words, it cannot be subjected to water. Sealing, ingress protection of 6, which is dust level. Fine dust can be protected here. And 4 is the spray magnitude that the sensor can sustain. acceleration, 500 meter per second square, the shock and vibration are specified. Also the mass and the cables and the communication format. Now here we see that the communication format is RS-422, RS-485. As mechanical engineers, we may not be familiar with some of these definitions, so we have to research them. We see over here that RS-422 is defined as the electrical characteristic of a digital signaling circuit that can transmit data at the rate of 10 megabits per second, and it's also differential transmission. And we also see the pinout. We can see that there are over here 9 pins with the data transmit designated TXT, the request to send pin, the receive data, and the clear to send. This is part of the specification of this particular transmission code. We also see the definition of what is differential signaling, meaning that we have 2 wires which pretty much carry the signal and the inverse of the signal. And the reason why it's being done is to immune the transmission information from noise. So if a signal is shown over here, like a velocity profile of a mechatronic axis, we see that the signal over here and the opposite of the signal are coming in here. And then a noise may interfere and may be added to the 2 signals. And then when we add the 2 together, we subtract the 2 together, the net result will be the actual signal and removing the noise which interferes with the signal. So that's a common way of transmitting signal with differential signaling. The technology of the sensor is also defined in the data sheets. We see over here in this particular case, there is a light source that has over here a diffractor that comes here to a beam splitter that goes to the target and then comes back into the sensing device. And the sensing device will increase the pulses as it goes from one line to another line. So the beams must be focused, and this is the hardware of the sensor itself. So this is the read head, and this is the scale. The scale has gratings, and the read head has the electronics and the mechanics or optics to transmit the signal to the sensor. We see here an example of a similar encoder that shows the principle of communicating it to the controller. So in this particular case, we have over here the signals are coming in with windows that are showing the let the light be transmitted or not be transmitted. So we have over here the sensors, and as the window hits the sensor, the light goes through, and we get the signal as long as the encoder is within this range. And then when the black portion comes in, then there is an off signal, on and off. And similarly, there is at a slightly different location, another sensor, similar sensor, that shows over here a similar signal, but it is offset by 90 degrees. So it's 90 degrees out of phase. These two signals often called the A quad B, quadrature signal. We see over here how we may control the system by incorporating the signals into a microcontroller. This particular one is the Arduino Uno, which we will use in the lab experiments. And we see over here that we supply voltage to the device and also ground from the source over here at the controller. And then we input the encoder A into pin number 2 and encoder B into pin number 3. And now what we do over here with the program, we have to define the pins. We define the communication rate of the signals from the encoder. And then we define here the program, which first defines the variables and then goes through a loop. And we notice over here that when the blue one is leading the green, such as in this case, then the signals are going to be exactly the same. We have over here that when this falls down, these two signals are the same. And when this falls down, these two signals are the same. It's either 1 or 0. And it is the otherwise when the two signals, when the green one is leading the blue. If this green is leading, we see that this one is plus and this is 0. This is 1 and this is 0. So the software takes that in account, and we see over here an if statement that if the state has changed, then if the A is different than B, then we add a signal, we means that we're moving forward, and if it is not, if it is equal, we subtract, meaning that it moves forward, and then we update. So this is the mnemonics that we have to learn for the program of whatever controller we're using, and then we have to connect the hardware, the signals, into the I/O terminal and write the program. We see over here an example of this program that we define the output signal at pin 6, the output of B signal at pin 7. We initialize some of the variables, and we also define the output A and B as inputs, and then we can continue with the program. The sensors that we are choosing have a vast number of manufacturers and options for us to choose from. So we, in this particular case, we look at the different vendor that provides a similar sensor, and this vendor is communicating through BISS interface, and there are several types of interfaces between the controller and the sensor. There's some which are open source, like BISS, and there's some proprietary, which is like Hyperface and NDOT. And this is a competitive data sheet of Heidenhain, another highly respected company that sells encoders, develops, manufactures them, and they're showing over here that they are communicated with the controllers with an NDOT interface. The other specifications show that the encoder provides a 1 volt peak-to-peak sinusoidal output, and there's a transistor logic is square wave signals, and various information is given there. And of course, we need to study the data sheets of the competing vendors and the sensor that we like to select, and of course that the selection should not be based on the cheapest option. There's a saying, we are not rich enough to buy cheap things. So the evaluation criteria is the performance, the reliability, Six Sigma, meaning that 1 part in a million will be defective. They like to see reference case studies for the application that we have in mind, the availability, technical support, international supply chain, documentation, open source software, sizing tool to select, demonstratings to test, return policy in case we have an issue, plug and play to minimize the integration time, wireless communication, accessories integration, phase out policy in case we have a large volume for many years to come. We like to understand the policy when the product will be obsolete, and then of course price and quality discounts. The product has to be supported throughout the life cycle of the program, including product development, beta site, meaning a small number of friendly customers that are willing to test our product, and then at the ramp up when we increase manufacturing, full-scale manufacturing, and phasing out. Here again, we see sensors in wireless communication arena. Here's the sensor, here's the gateway. It goes into an online cloud, and then it is set up into a accessible monitoring devices such as cell phone, a laptop, or a PC to give us the information, statistics, and perhaps allow us to send back feedback to the actuators near the device in order to complete the feedback process. The sensor wireless range defines the type of protocol that we'll use, less than 50 feet, commonly used by Bluetooth. We have 120 feet, Wi-Fi, and there are also other protocols that could be available when we are using the communication wireless to longer close-by intervals. We have also accessories, routers, and various other devices that we need to understand from the vendor when we decide to buy their sensors. Over here we see a National Instrument providing us an extensive data management of Internet of Things technology. And the information is enhanced with, for example, devices such as augmented reality. Not only that we find out where is the problem, where we get the red signal on a display, we may also find out the detailed point how it may be corrected when the problem is sensed to exist in one of the equipment. LabVIEW also has analytics for machine learning as a toolkit. We see that it's selling for approximately $2,000 and can be downloaded and be used to teach the machines the data that we know the objective functions for, and then use the trained machine in order to detect problems with data that we are not there available to rate it. The question is who is in charge of the operation technology and the internet technology, including hardware, software, networks, and database. As mechanical engineers, we are not trained extensively to solve problems, and many times we are involved with operation technology, where we are in charge of maintaining the systems that we develop and assure that they run in good conditions. And the solution is that IT and operation technology must take partnership to new levels. And it says over here that 72% of edge computing initiatives are started by operation technologies, where mechanical engineers may take an integral part of it. This is done by, shown by Inter. And the operation technology engineer job description is shown over here. And this is overseeing the general technical process in engineering or industrial and establishment to ensure optimal performance. They take care of facilities such as compressor, power system boards, refrigeration, and many other ones. The AI data insight is that by provided by Intel is that by 2022, as a result of a digital business project, 75% of the enterprise generated data will be created and processed outside traditional central data centers or the cloud, up from less than 10% in 2018. So the data that we collect from sensors is going to be distributed into clouds and also into an edge. Cloud meaning a distance location from the place where the sensor is being collected, and then it's analyzed in a cloud, and an edge is where it is in close proximity. And the entire process is going from sensing to learning to thinking and reacting with an increased intelligence. The skill sets that are expected from a mechanical engineer when they are taking action as operational technologies is such that they will be familiar with the IT decision process and take integral part of it. And the messages to graduate AMEs with interest in mechatronics is to continuously learn skill set enrichment through online self-learning. This completes our presentation, and we'll continue with the program as shown in the textbook in upcoming lectures. Thank you.